Yeah. So let's say we have a wire loop. And we have an EMF in this wire loop. Jacob,
What does that even mean?
You remember like wire loops, EMFs, Ohm's law, V equals IR.
Electromotive force. EMF?
Maybe we have a resistor.
I remember Ohm's law.
EMF is just voltage.
Oh.
Yeah. So, you know, charge flows from negative, or the current flows from positive to negative, I guess. Conventional current goes this way in this circuit. But let's say we have a switch here. And we close this switch. We've previously assumed that once we close this switch, current will instantly start flowing in the circuit.
Mm-hmm.
In reality,
Oh my god.
nice. No, I'm just wondering. In reality, current doesn't instantly start flowing. And that's because of magnetic fields. So yeah, V equals IR will always apply. But when the switch is closed, it doesn't instantly start flowing current. And let's look at the reason why. So what would the magnetic field look like if current is flowing clockwise through the circuit?
Into the screen. Into the whiteboard.
We have it
Into
like
the
this.
whiteboard.
Into the whiteboard? Yeah, sure. I don't know how you did that, but okay. Sorry. That's I can never remember. Damn it. X, okay. X. And then, you know, we have current this way too, and it'll also be X's. So essentially, this current created by the connection of the battery will induce a magnetic field. And that magnetic field will in turn induce a electromotive force going the opposite direction in the circuit because of Lenz's law. So we have E equals negative d n d theta dt. Okay. So we're gonna have this electromotive force that's going this way. This electromotive force. And then we're gonna have an induced one which goes the opposite direction as the current is increasing. So that's conceptually also very confusing. How does an electromotive force start as the current's changing? Because wouldn't that make the current not change? Like if we have 0 volts, then why is the current changing at all? But okay, so let's figure out why this happens. So we have a current that we're trying to get to. If voltage is 5 volts here, and this resistor is 10 ohms, then with our previous understanding, we just have the current would instantly be half an amp. But the thing is, now we have this other electromotive force going on. So our total voltage is going to be V is equal to the EMF minus the back EMF, or EMF induced. So because current is proportional to, current is proportional to this magnetic field that's induced, and that's proportional to the total amount of magnetic flux. Right? As current starts flowing in the circuit, a magnetic field will appear from the current, and that will mean magnetic flux inside the circuit will appear. So that means the derivatives of all of them will also be proportional. di dt is proportional to dB dt is proportional to d flux dt. And therefore, we also have this equation, d flux dt is proportional to induced EMF, which means that induced EMF is proportional to the derivative of current. So as current starts changing, starts going up to the target current from 0, the derivative of current, it can be proportional to the induced EMF, which is really the reason why the current has to speed up in the first place. Again, V equals IR is always fulfilled, but the thing is, now that V is equal to E minus E induced, like at the beginning, we're going to have 0 volts is equal to IR. We're going to have some curve from T0 to TF, I0 to IF, this is just 0. We don't really know what this curve is yet, but it has to get from no current to some current somehow. And this law will always be obeyed. This law will always be obeyed the entire time. So induced current is proportional to di dt, and we're going to call that factor L, and we'll get to why that is in a minute. But we're going to call E induced is equal to di dt times L.
What is E induced again?
E induced is the back EMF. It's this backwards electromotive force that opposes the battery thing as current starts to speed up. Because current is being created by the battery, which creates this magnetic field, the magnetic field creates a change in magnetic flux through the circuit, which creates a backwards voltage throughout this whole thing. Okay, so E induced is equal to that, and the differential equation. Using this, V equals IR, E minus E induced, or epsilon minus epsilon induced, epsilon minus, we substitute this in, LdI dt is equal to IR. So we're going to turn this into a time constant equation in a couple minutes. But essentially, when at the beginning, when the current is equal to 0 amps, that's because if we rearrange this, I is equal to E minus LdI dt all over R. Initially, the current is going to be 0, and that means that EMF minus the back EMF is also going to be 0. So the back EMF is going to be equal to the battery. So these arrow vectors are going to cancel out. There's going to be no electromotive force at the beginning because I is 0, even though, you know, we have this battery going on. But the total electromotive force is 0. But that's because the current is changing. The current is currently 0, but it's increasing. di dt has to be positive in order for these EMF values to be equal to each other.
So it has to be a...
not logarithmic, but an exponential there.
No, it's going to be a time constant, similar to capacitors.
Damn.
Yeah. So it feels like we're taking something out of nothing, but this differential equation is a weird way to model it. But yeah, current is going to plateau like this, starting from 0 amps all the way to like the total current as time goes on after the switch is closed. Again, the switch is closed. The circuit attempts to create a current because it has now an electromotive force pulling the current, but instantly a magnetic field is created by this changing current that creates a backwards EMF, in the sum of those voltages will be equal to IR here. The current is going to follow the EMF, and that's going to follow the change in current, which is all a mess, but it ends up being this time constant equation. Hope that makes sense.
What does
I don't even know what to
start
write
writing
down.
I don't know what to write
Okay,
down.
all box important thing. This is, okay, so box of V equals IR, because this is always true. V is equal to EMF of the battery minus EMF induced, because this is the back EMF created by Lenz's law. We have E induced is equal to L times DIT, and then this is the final thing here, and then I guess you can make sure this equation's at the premise, and I guess this is more too.
What does the induced mean in epsilon induced?
It's an induced EMF. Remember we just learned about induced current coming from a change in magnetic field?
Oh,
It's an
yeah.
induced current change in magnetic field, or induced EMF by change in magnetic field, and that change in magnetic field comes from the current that's being created in the first place.
Because there's all those X's in the circuit.
Yeah, all these X's, these are the change in magnetic field.
What if there wasn't?
Well, these are created by the current
Yeah.
that's coming from in the first place.
The change in current is proportional to the change in magnetic flux, right? Or is the magnetic? Okay, yeah.
Yeah, exactly.
Yeah, okay. That makes no, that's obvious. So
Okay.
is inductant? I mean,
Okay, wait. Okay, so L, you're getting ahead of me.
uh-oh.
L is inductance. Inductance is a measurement for how strong this relationship between the change in current and the back EMF is. And in this circuit, the magnetic field being created by those wires, this is just like the natural inductance of the loop, and we call that self-inductance. Because like, it's just itself doing the inducing. But you can concentrate this change in magnetic field by adding a component called an inductor. So this is an inductor, and the inductor has an inductance value that will make this time constant part of the circuit change drastically.
What is the definition of inductance again?
It's the proportionality constant between induced EMF
Yeah.
and
I mean,
derivative of current. That's its only definition.
That's its only definition.
That's really its only definition, yeah. Unfortunately.
Okay.
Yeah.
Of how inducting an inductance is.
Right, so you have an inductor, which is like a coil of wire.
Yeah.
And a bigger coil of wire that has more inductance will make it harder for current to change in a circuit.
Okay.
It doesn't impede current like a resistor, it impedes the change in current. It's like a derivative resistor. So yeah. Okay. So the prime example, of an inductor is a solenoid. And we learned about a solenoid last time. It's a component that creates a lot of magnetic field from a current. So this is what a solenoid is, what an inductor looks like typically in a circuit. And we know that the magnetic field of a solenoid is equal to mu times little n times I. So recap, this is permeability. This is turn ratio. So number of turns per length. And then this is just current. And we want to turn this equation into the inductance. We want to try to solve for the inductance of a solenoid. And the way we do that is by combining this equation. So we're looking for di dt times something rather is going to create this.
Wait.
EMF.
Is B, what is B?
That's magnetic field.
Okay.
So we know that epsilon is equal to negative n d flux dt. And we know that flux is equal to integral BA, or dot product, BA. Okay, let's erase this.
No.
So with all these equations, now we just do a bunch of substitution. So we have, if we use this on the left side and this on the right side, we have negative n d flux dt is equal to di dt times L, and we're looking for L, remember. Flux, magnetic flux, is equal to integral BdA, and we can just simplify that to BA because it's a uniform area and a uniform magnetic field through a solenoid. So now we have negative n times the derivative of BA dt equals L di dt. Alright. So next, area isn't changing with respect to time, but magnetic field is changing with respect to time. So if we substitute all of this in for B, we get negative n times the derivative of mu n I a over dt equals L di dt. Jacob, how do you think we continue from here to solve for L?
You divide
You divide?
Huh?
by di dt.
Okay.
You got it all on one side.
Yeah, but first, can you like turn this equation into di dt? Because we don't have di dt on the left side, do we?
What?
Where's the di dt on the left side? I mean, it's in here, but what do we do about these things?
Shovel them out because they're all constants.
Integrate?
Yeah, we just pull them out, the constants.
Oh.
So we have negative n mu a, and then another n. Oh, sorry. This is a little n. So all that shenanigans there times di dt equals L di dt. Okay, Jacob, now what do we do?
Now you divide.
Now we divide.
Yeah.
Why did I write two D's? Wow, I'm done. Okay.
And then
L
n equals n over L.
Yep. N mu a n equals n over L. This is a different L. This is inductance. That's length over there. So we have, and we can get rid of this negative sign because it doesn't matter.
What?
It's an inductance, which is a positive value always. And we just stuck that in because of Lenz's law. So inductance is equal to
For a solenoid.
little n turns inductance for a solenoid.
Oh, dude.
Is
What's
gonna be
solenoid
this,
again?
this n
So this-
changes into n
Is
over
the
L.
twirly thing a solenoid?
Yeah, n squared mu a over L.
It's a lot different than what I have written down.
Or n squared L mu a. because this N, the little N is big N over L. So you can just substitute, choose which one you want to use. And you can also, if you want to, area equals pi r squared. So then you have pi r squared N squared L mu. It's a ridiculous formula.
What is A?
A's area.
Oh. Area of what?
Area inside solenoid.
Inside of the solenoid. Because like, think about the magnetic flux inside of the solenoid. It's just B times A.
Like a cylinder?
Yeah. So it's like a coily thing.
Yeah.
And the area, like the cross-sectional area, that's the flux.
Oh.
It's sort of like a cylinder.
Okay, and then mu is permeability.
Permeability to free space, yeah. Or whatever material is inside the solenoid, which does change. So yeah, you can derive the inductance of any shape object, but typically a solenoid is what's used for an inductor in a circuit. So yeah. Okay.
So an inductant or a solenoid just twirls the current around and then makes it all do all this shit.
Yeah.
Okay.
By twirling this current around, it makes a really strong magnetic field, and that magnetic field will fight against all these wires, pushing the current in the opposite direction, which makes more inductance, harder for current to change. So back to where we were. Here we have a circuit with a battery, a switch, a resistor, and an inductor. And we, a minute ago, talked about how the magnetic field makes the current slowly transition instead of instantly turning on. So that just follows a time constant equation, but we're going to do the derivation for that, again, even though we've done it already for capacitors.
So what? Do you need a switch for this?
The switch just represents that it turns on at a specific moment, right? Because what matters is
What about
the
if it's
change.
already on? Then does happen?
Right. So if the current's already constant, if we already have a current going through the loop at t equals 0, is if I is like, I don't know, let's say this is 10 ohms again, this is 5 volts again. If current's already 0.5 amps, the inductor does nothing.
Okay.
Well, a perfect inductor doesn't do anything.
You mean because it might have resistance? Well, yeah. So this will already have.
Wait, isn't that what
magnetic
isn't that what a resistor is already?
No,
Oh.
resistor resists current. Inductor resists
But I
changing
thought
current.
resistor was just a ton of wire.
Right. No. It's a really thin wire.
Oh, is it?
Yeah. And a solenoid or inductor is like a spirally wire. A solenoid.
Okay.
Yeah. It's a good question. The inductor only does stuff when the current is changing. But yeah, so we have the equation EMF of the battery minus EMF induced is equal to LdI dt. Oh wait, no. EMF minus LdI dt is equal to IR. This is our equation for, this is just a V equals IR. We start Ohm's law. And we're going to do the same time constant derivation that we did with a capacitor. All right. So we divide both sides by R. E over R minus L over R di dt is equal to I. Great.
Wait, so doesn't that mean that a capacitor has inductance?
No.
Huh?
Capacitor does not have inductance. I mean, all materials will have some measurable inductance, but an ideal capacitor does not need to have inductance. The reason that capacitance has a time constant is completely different. It's like a charging capacitor it's a change in EMF, but it's because of a different reason. We subtract EMF over R from both sides. I minus EMF over R equals negative L over R dI/dt. We flip both sides of the equation so we can rearrange it the way we want. 1 over I minus EMF over R equals negative R over L dt di, and we move di up here. Now we integrate both sides. We also know that at t equals infinity, we'll just have E equals IR because the change in current once we're at a steady state is going to be 0. So like at the final point, when inductance no longer matters, we just have V equals IR, like we always did. And therefore, I final, or also called I max, I at infinity will be equal to E over R, or sorry, epsilon over R. It just looks like an E, I'm sorry. So we can change this to I max. So we integrate both sides from t equals 0, or sorry, okay, so the bounds of this one are t equals 0 to t equals tf. So the bounds from here are I equals initial current to I equals current. I equals I. current. So we have ln of I minus I max from I initial to I is equal to, what's the integral of negative R over L dt? Raja?
It would be negative R over L t.
Yep. Negative RT over L t equals 0 to t equals tf, which is t equals t, I guess. So expand this to ln of, so because when we do ln of this minus ln of this, and then when you do subtracting ln's, you can just divide the insides. We have ln of I minus I max over I initial minus I max. And that's equal to negative RT over L minus 0. So negative RT over L. And then we do e to the both sides. Get rid of this. Get rid of this. Equals e to the RT over L. Finally, we multiply both sides by I initial minus I max. So I minus I max equals I minus I max e to the negative RT over L. Let's rearrange this.
Yeah, that makes sense. Is this something we should write down?
We already have this derivation written down, but you can write it down again, I guess. If you want.
Oh, real?
Yeah.
When did we? Oh, yeah. No, you right. My fault. Actually, I don't think I wrote that down.
So this rearranges somehow into I equals I max minus I 1 minus e to the negative RT over T, or I mean over L plus II. This is the same formula, we just rewritten with the 1 minus. And this formula is of the time constant form. So the time constant general formula is change equals final minus start one minus e to negative t over tau. So in this situation, we have our change in variable is I. If we move this to the left side of the equation, we get I minus I. So that's the change. This is the final minus start, and here's 1 minus negative t over tau. So for an an LR circuit, what's the tau equal to? What's the time constant equal to?
Would be negative. Oh no, it'd just be R over L.
We got it again. Jacob, see if you can beat him. We have this equation, we have this equation. These are the same equation. What would the time
Oh, it'd
constant
be
be?
L over R.
Is that right, Jacob?
I don't even know what he's talking about.
So
What's tau, bro?
L over
Trust,
R?
trust.
look, so we have RT over L, and we have negative t over tau.
Oh, what is tau? Oh,
Yeah.
negative. It's R over L.
Close. Because tau is divided.
Oh, L over R.
L over R, yeah. Great. So this is the time constant of a
What is a time
LC
constant?
circuit, or LR circuit. It's the amount of time it takes to get 63.2% of the way closer to the change.
What? 63.2%.
Yeah, it's 1 minus e to the negative 1.
Oh.
So I did this earlier. I max
63.2%.
I0, and then here's one time constant, and we're at 63.2%. After another time constant, now we're at another 63.2%, which keeps getting closer and closer. It's like a half-life, except it's 63.2% and 60%.
But why? Why can't they just
Because-
do half-life?
You can, but it just works out easier for the differential equation because you don't have a coefficient.
Yeah, I see.
Alright, so the takeaway from this is the time constant of an LR circuit is L over R. That's it.
Oh, because it's 1 minus e to the negative 1.
Yeah.
Bro.
Yeah.
Oh. Dude, that's crazy.
1 second.